Hello students, welcome to the second video lecture on advanced power electronics. We were studying resonant converters. I taught a few basic ones in the previous class. Today we are going to see the remaining two ones. Once again, this is going to be a short video, only 5 to 10 minutes, not more than that. Today the first converter that we are going to see are the resonant DC link inverters. In the last class, we saw the resonant switch converters. These are resonant DC link converters or resonant DC link inverters, wherein, as you can see, the supply is still DC and this I0 represents the load. Between the supply and the load, a resonant circuit has been introduced, which comprises of LR and CR. RL represents the losses in the resonant circuit, which we can discard for now. Once again, we are studying only the basics here, so no need to go into the details. So a resonant circuit has been introduced between the supply and the load so as to obtain zero voltage switching. What happens here is, initially, this switch T is closed so that the current starts building up through this path. And as soon as the current IL becomes equal to I0, this switch is opened. And then resonance is introduced in this circuit through the path LR and CR. What will happen here is the voltage will fluctuate between 0 and a maximum value. So that whenever the voltage is 0, switchings will take place in the inverter circuit. That is inside the I0. So in this resonant DC link inverter, you obtain zero voltage switching because of the resonant circuit introduced between the supply and the inverter. Once resonance has been established, this switch and diode can be removed. In fact, if you have an inverter circuit here, the initial building up of current through LR can be done through the inverter switches itself, and this switch is not required. The last type of resonant converter that is there is the high frequency link integral half cycle converter. This is one example of a high frequency link integral half cycle converter, wherein you can see that the major difference is that the supply is now AC. In fact, the supply is high frequency AC. A high frequency AC supply is required for this type of converter. The switches that you see are bidirectional switches. You must know already that bidirectional switches can be made by combining two unidirectional switches in anti-parallel. In this case, what can be done is, as you can see, there are three waveforms here for positive output current. The current can be positive as well as negative here. During the resonant cycle, if we assume that the output current is constant, here there are three possible outcomes or three possible output voltages. In the first case, as you can see, the output voltage is positive in both the half cycles. In the second case, the output voltage is negative in both the half cycles. And in the third case, the output voltage is 0. For the first case, the switches conducting are A plus and B minus during the positive cycle of the supply voltage. So when the supply voltage is positive, upper terminal is positive, lower terminal is negative, you are switching on A plus and B minus. So that if the output current is positive, the current flows from the supply through A1, load, B, B minus, and back to the supply. That means your point A is connected to positive of supply and point B is connected to the negative of the supply, so that your output voltage V0 will be same as the supply voltage, as can be seen in the first half cycle here. During the negative half cycle of the supply voltage, the switches that are turned on are A minus and B plus. Now, because the supply voltage is negative, the lower terminal is positive and the upper terminal is negative, so that when you are turning on A minus and B plus, the current flows from the supply through A minus, load, B, B plus, and back to the supply. Now remember that the supply voltage is negative. That means the lower supply terminal is positive and the upper supply terminal is negative. So A is once again connected to the positive and B is connected it connected to the negative, so that once again your output voltage is positive even though the supply voltage is negative. The lower waveform, you can see the supply current. When A plus and B minus are conducting, the supply current is positive. A plus and B minus conducting, the supply current is positive. Whereas when A minus and B plus are conducting, the supply current is negative. If you want the output voltage to be negative in both the half cycles, the switches to be turned on are A minus B plus during the positive half cycle and A plus and B minus during the negative half cycle. And if you want zero output voltage, you are turning on either A plus B plus or A minus and B minus. So basically you can have either positive output voltage in both the half cycles, or you can have negative output voltage in both the half cycles, or you can have zero voltage in both the half cycles. So this concept can be used, for example, in synthesizing this type of waveform. This is the input voltage, which is a high frequency AC waveform. This is the reference output voltage. Now, when you want the output, or when the reference output voltage is positive, as you can see, the switches are controlled in such a manner that the output voltage is positive. And when the reference voltage is negative, or you want the output voltage to be negative, you are turning on the switches in such a manner that the output voltage is negative. You can introduce zero voltage segments in between to control the magnitude of the output voltage. So this is what is called an integral half cycle resonant DC link converter. I think the name is self-explanatory. So here we end the other types of resonant converters which were not in our syllabus, and we were just seeing them or looking at them for us to have some knowledge about them. In the next lecture, we will go into the series resonant converters and the series loaded resonant converters and the parallel loaded resonant converters in detail. Okay. That's all for now.